So, we're going to work on Lewis structures, and we're going to work on one for carbon dioxide. So, we have a step-by-step process of what we're going to do, and you got to know what the steps are, you got to know what you got to do with each step, etc., etc., etc. All right, now the first thing, if we're doing this totally formally, and this is going to work for every single one that you have, the first thing you have to do is find the number of valence electrons in total. Alright, so here's what you got to do. For carbon, how many valence electrons are there for carbon? There's 4. For oxygen, how many valence electrons are there for oxygen? There's 6, but we have to multiply it by 2. Why would we have to multiply it by 2? Yeah, because there's 2 oxygens. So there's 12 there, and what you do is you take the 4 plus the 12, and we get 16. So what you do is you take all the valence electrons that are available to you and add them all up. That's your first step. Second step is you have to determine the number of bonding pairs. And what you do is say to yourself, all right, how many electrons are in a bonding pair? When you put that bond in there, how many electrons are there? 2 electrons. So, you take the 16 total electrons, divide it by 2, and that tells you how many pairs do we actually have to bond with. 16 divided by 2 is 8, so we have 8 pairs. So figure out how many total valence electrons you have, then take that number divided by 2, and you have 8 pairs. All right, 3. Draw in the single bonds. Now, since we have carbon, carbon goes on the inside. Oxygen is going to go on the outside. Oxygen is going the outside. And we're going to bond those two together with single bonds. Now, how many bonds did we use? Okay, so we used used 2 bonds. So you take the 8 that we can use, subtract off the 2, and we have 6 left over. Now, these oxygens are referred to as terminal oxygens. So what we're going to do is we're going to take the 6, and I'm going to put 3 lone pairs here, and 3 lone pairs here. Now, at this point, once you fill them in, how many lone pairs did I use in total? 6. So I had 6 left over. So 6 minus 6 is 0. So that tells me all electrons are used up, which is good. But now, since all electrons are used up, check each element for an octet. Does oxygen have 8 electrons? That oxygen has 8. Does this oxygen have 8? How many does this carbon have?
2.
Not 2. 4.
Oh, because the line is like 2 connected.
The line represents 2 electrons. So carbon only has 4, but how many does carbon actually need? For an octet, how many does carbon actually need? 8. So what we're going to do is, we're going to take a pair from each one, and we're going to make another bond. So we're going to take the carbon, and now it's going to be a double bond to oxygen. And since we used one of the lone pairs from here, I'm going to use the other 2 lone pairs around oxygen. And I'm going to use the other lone pairs around oxygen here. Now we can go back and say, all right, do I have 8 electrons around this oxygen? There are 8, because each bond represents 2. So there's 2, 4, 6, 8. Now this other oxygen, 2, 4, 6, 8. Now if I cover up these, 2, 4, 6, 8. This is how you want to approach every single Lewis structure. If you do it this way, you'll get it 100% correct 100% of the time. You find the number of valence electrons in total, so you have to count them up, so that's where your periodic table is going to come into play. Divide it by 2 to figure out the number of pairs that we're going to be able to have. Draw in your single bonds to start with. Remember, carbon always goes in the middle. Hydrogen is always going to go at the end. Then subtract off the number of used bonds, and that'll tell you how many pairs are left over. And then you start filling in the outer, the terminal elements to make sure that they have the octet. But then you check to see, all right, does that element in the center have an octet? And if it doesn't have an octet, we can move the lone pairs over to become bonds. And so that's how we determine if there's going to be a double bond or maybe even a triple bond. Does that make sense?
Yes.
All right.